All right. First thing we'll talk about as far as addition is concerned is just problems on a number line. If we want to add -4 plus 7, and -4 plus 7 is going to equal 3, but if we want to see what that looks like on a number line, we'll draw a number line that goes forever in both directions. 0 is a really important number to have on there, and you can do a problem like this on a number line in a couple of different ways. One way is to look at each of these numbers individually and say, okay, I'm starting at 0 and I need to go -4, so I'll go back 4 from there. That's the -4 part, which puts me here at -4. And then after I've done that, I will add 7, which means I'll go to the right 7, and that puts me here at 3, and then that's the answer to the question. And that's what this could look like on a number line. Another way you could do this, I kind of like that way where you show both numbers, but another way that it's perfectly okay to sort of diagram a problem like this is to say, well, we're going to start at -4, and since it's +7, we're going to go to the right 7 from there. And you just start at -4, go to the right 7, and end up at 3. Either one of those is a perfectly good way to represent a problem like this on a number line. Whichever one you like better, honestly, whichever one works best for your students. If it's better for them to see the -4 happen on the number line, then do that. If they get to a place where they're comfortable just starting at -4, then maybe you can leave that step out. All right, properties. These are some properties of addition. We're going to talk about these properties as we continue through the operations, but we're talking about addition today, so that's where we're going to start. And the first property we're going to look at is the commutative property. I don't know if you've had a chance to read the weekly update that was sent out earlier today, but this is one thing that does sort of get under my skin a little. Not very much does. I'm generally pretty easygoing, but one thing that definitely drives me a little bonkers is when people call this the commutative property. There is no commutative property. It doesn't exist. There is not a commutative property. The property is the commutative property with a T over here, and that T is very important. The root word here is commute, which is to move. If you commute when you go to work or you commute when you go to school, you are moving from one place to another. We're changing your position. We're changing your location. There's nothing community about it. It's strictly, we are going to move something from one place to another. Please do not use commutative. Not only does it make my skin crawl a little bit, but it kind of shows that you really don't understand what this property is. And that's no good at all. So please make sure to use the correct name for this one, and that's commutative. Okay, that's enough of my nagging for today. The commutative property is about order. An example of that would be that 7 plus 3 gives us the same result as 3 plus 7. We can add those numbers in any order we want to. When we change the order of the numbers, but we're adding them, it doesn't change the result. Both of those are worth 10, so either one of those is just fine. The sort of generic way that we're going to write this, just to state it as a property, is that A plus B is equal to B plus A. That's the commutative property of addition. As we go through these, please let me know if you have any questions about any of them. The next one is the associative property. And the associative property is about grouping. Which numbers are grouped together? An example of this would be 2 plus 3 plus 5, and that's going to equal 2 plus 3 plus 5. Just to make sure this is true, let's take a second and do that. So order of operations says I do parentheses first, so I get 8, and then I need to do 2 plus 8, which would be 10. On the right-hand side of equals, 2 plus 3 would make 5, plus 5, which, okay, that's 10. Okay, so that is a true statement that 2 plus 3 plus 5 in parentheses is equal to 2 plus 3 in parentheses plus 5. That's a true statement. And what's happened here, what's changed here, what is different is on the left, the 3 and the 5 are grouped together. On the right, the 2 and the 3 are grouped together. It's the grouping that has changed. You'll notice the order is the same. 2 plus 3 plus 5, 2 plus 3 plus 5. The order didn't change. If the order changed, then it'd be about commutative property. But the order didn't change here. What changed was the grouping. And when the grouping changes, then that's an example of the associative property. The way that we'll write this to be generic is A plus B plus C will equal A plus B plus C. And that's the associative property because it's about grouping. Finally, the identity property, which may feel a little obvious to you, and that's okay if it does, but the identity property is 7 plus 0 is equal to 7. In addition, we would call 0 here the identity element. You're not going to really need to know that, but if it ever comes up for you down the road, the identity element is the thing you would add to a number and still without changing the value of that number. So with addition, that's going to be 0. So we have an identity element. One thing you'll notice over here in my little note about this is that it must work both ways. What I mean by that is in order for us to have an identity property, 7 plus 0 has to equal 7, and then we have to be able to use commutative here and say, what about 0 plus 7? Yeah, that's still 7. So it works both ways. When I say it has to work both ways, that's what I mean. The 0 could be the second number, or the 0 could be the first number. It has to work both ways to have an identity property. It does here, so we have an identity property. Just a little refresher. Commutative property is about order. We can change the order, and the value stays the same. Associative is about grouping. We can change the grouping, and the value stays the same. And identity is is there a number we could add without changing the value? And it has to work both ways. One thing I didn't put here is A plus 0 equals A is the generic way we would write that, knowing in the back of our head that 0 plus A has to equal A also. It has to work both ways. Let me know if you have any questions about this before I have you try a question that involves the properties. All right, great. Here goes. What property is shown in the equation below? Be careful. I'll make a poll for this. I say be careful because I don't want you to look at this like a trick question. I want you to be careful. Go another 15 seconds on this, and then we'll talk through it. And what property is shown is a great way to ask questions like this. All right, let's see how we did. Okay, pretty much split. We don't have strong agreement here. To be honest with you, it's kind of what I expected. You could make the claim that this is a trick question, but that would be a hard sell for me. The key here is, what is it that changed? Obviously, it's not about the identity property because there's no 0 in here. We're not adding 0. So this is really a there are two possibilities here. Is it commutative, meaning the order changed, or is it associative, meaning the grouping changed? Well, let's take a look then. Let's see. The order goes 1, 4, 6, 4, 1, 6. Well, the order definitely changed. I'll keep that in mind. And then the grouping, 1 and 4 are grouped together, 1 and 4 are grouped together. The grouping did not change. This is definitely not associative. This is an example of the commutative property. And the trap that you fall into here is thinking that the associative property is about parentheses. It's not. The associative property is about grouping, not parentheses. So just because you see parentheses doesn't automatically mean that must be associative. No, step back, take a little more time than that and say, wait a minute, what is it that's changed here? If the order has changed, which is true in this problem, then it's commutative. If the grouping has changed, it would be associative. The grouping didn't change here. So just because you see parentheses, don't have an automatic reflex to associative. That's not necessarily the case. Let me know if you have questions on that. Okay. Some important sets. Back when we were doing set theory and we talked about using capital letters as the name of sets, we saw this, but just to sort of revisit it for a minute. The natural numbers we abbreviate with a bold-faced N, and I can't really make a bold face with a pencil, so we'll write it that way, a bold-faced N. And the set of natural numbers is the ones that you could count on your fingers. So that's 1, 2, 3, and it keeps going on forever. The set of whole numbers, we use a bold-faced W, and that set is, well, it's the natural numbers, but we also throw in 0. Easy to remember, 0 kind of looks like a hole. So the whole numbers are 0 and the natural numbers. So we're kind of building these up as we go. And then the integers, you may remember that I has another purpose as far as imaginary numbers go. So we use a capital boldface Z for integers. And integers, sort of a nice working definition is integers are the whole numbers and their opposites. So it's all of these numbers and then all the negatives that go with it. So it goes back to negative infinity and then -2, -1, 0, 1, 2, and off to positive infinity. And that's the set of integers. We have a topic coming up where we're going to use natural numbers, whole numbers, and integers in that topic. So I want to make sure that these are comfortable for you before we go forward. Let me know if you have any questions about any of those three sets. As you studied numbers in the past, you may have seen rational numbers and real numbers, and they're definitely important, but not so much for our class. We're going to stick with these three sets. Okay. Closure. This is an idea that may be new for you. Closure is basically, think of it as whether or not a certain system is closed. Is it constrained within itself? An example of closure under addition. Well, not necessarily an example. The definition of closure under addition is if we add two numbers that are in a certain set, the result is also in that set. And so we want to find out whether or not this works. And so this question on this page just says, is the set of whole numbers closed under addition? Essentially, what we're looking at here is a true-false question where the set of whole numbers is closed under addition. All right, well, I'm going to see if I can find an example that would make this false. So I'm just going to try some. All right, I want to add two whole numbers. So let's try 5 and 8. I get 13. Yeah, that's a whole number. So I got whole number plus whole number gave me whole number. So in this example, and this is just one, but for this particular example, yes, it's closed. I started with two whole numbers. I added them together and got a whole number as my answer. So it's closed. For that example, if I want to say no to this question, I just need one example that shows it false. So I'm going to spend a little more time seeing if I can find one example that makes this false. And if you come up with one, you let me know. Let's see. Well, whole numbers have a 0 in it, so maybe I should try 0. How about if I do 0 plus 2? That would be 2, and that's whole number plus whole number equals whole number. Yeah, that's closed. And gosh, what if I do, I don't know, like 17 plus 3? Yeah, that's whole number plus whole number is whole number. You know what? I'm not going to be able to find one. I'm not going to prove that this is true. I'm just going to sort of convince myself by exhaustion that, you know what? No matter how many, when I add whole numbers, I'm always going to get a whole number back. So the answer to this question here, is the set of whole numbers closed under addition? Our answer would just be, yes, it is. Do you have questions about this before I let you try one? All right, here goes. True or false? The set of integers is closed under addition. I'll make a poll for this and let you try it. Just a simple true false. The language here, the set of integers is closed under addition. What that means is if you're doing the operation of addition, is the set of integers closed? So under addition means doing the operation of addition, is the set of integers closed? Part of this is a new term that we've probably never seen before a few minutes ago, closure and closed. And then part of this is getting used to, if I want to decide if something's true or false, the best thing I can do is try to show it's false by coming up with an example. And if I can't come up with an example, then I kind of convince myself that it's true. Go another 20 seconds on this, and then we'll talk about it. Let's see how we did here. Okay, split again, 2/3, 1/3, but still definitely split. Before we approach this, if you decide this is false, how did you decide? What is it that convinced you that this was false? Somebody who said integers closed under addition, that's false? How'd you come to that conclusion? What's the counterexample that you came up with to convince you that this would be a false statement? You don't have to type it in there for me, but you can if you want to let me know how you decided this was false. Here's how I decided, because of this thing right here. The way we'll decide is we'll just try some. I'm going to add some. Oh, cool. Let's see what Will comes up with for us here. Okay. Oh, that's honest, Will. I'll take it. Definitely not 50-50. There's definitely a way we can decide. If we're going to say this is false, then we need to be able to say, here's why I think it's false, is because I can add two integers and get something that's not an integer. So as we investigate this, so I'm going to take an integer and add it to another integer and see if I get an integer back. Sure enough, that's an integer, that's an integer, that's an integer. Well, yeah, you picked positive numbers. What if you use negative ones in there? All right, let's use some negative ones. How about -4 plus 9? Get +5. That's an integer, that's an integer, that's an integer. So far, I'm feeling like anytime I add two integers, I get an integer back. What about two negatives? Okay, -6 plus -5, that would be -11. And it's true, they're all negative numbers, but that's an integer, that's an integer, that's an integer. Pretty much convinced that anytime I add two integers, I'm going to get an integer back. Okay, good point, Madison. And thinking that is reasonable. Then what you have to do is try some and see what happens. Because if you're going to say false, it should be really easy to sort of make that assertion based on, oh, because of this thing right here, that's what makes it false. Kind of like if I were to say it's always sunny in Las Vegas. You can kind of get away with saying that, but mathematically, if you could say, nope, on January 11th last year, it was raining. Well, that throws always right out the window because always means every single time, no exceptions. And here, if I'm going to say this is true, that means every single time, no exceptions. If I can find an example that wrecks this, then I can say false. But if I can't, and in my work to try to find one, I kind of convince myself that it's true, then it's true. We're not going to do any formal proofs, but we can convince ourselves that it's true. Oh yeah, I didn't do any with 0. So we could have -12 plus 0 is -12. Here again, that's integer, integer, integer. So the set of integers is closed under addition. Yes, it is. That's a true statement. Let me know if you have any questions about closure under addition before we move on from that. All right. Algorithms. We're going to look at several different algorithms today. And before we do that, I want to sort of define what an algorithm is. We hear about it all the time in the social media world, but basically an algorithm is just a clearly defined method that's repeatable. And as far as we're concerned, we need it to work in all cases when we're going to use it with addition, for example. We need our algorithm to work every single time. Otherwise, it doesn't have much value to it. But there are other things for algorithms. Brushing your teeth. Okay, you get your toothbrush out and then you put toothpaste on it, then you get it wet, you brush your teeth, you rinse it off, you rinse your mouth. Step by step by step by step. Clearly defined method. You do it every single time. That's an algorithm. Making a sandwich. Get out a couple pieces of bread. Put whatever you're going to put on there. Close it up and then you can eat it. That's an algorithm because you do the same thing every single time. It's a clearly defined method that's repeatable and you do it over and over again. Those are algorithms. And now we're going to look at algorithms for addition. The first is just our standard algorithm for addition. The way that almost all of us were probably taught how to add numbers. If we were to take, say, 369 and add it to 478. Now, we've done some of this already. We did it in other bases. Now we're looking at it from base 10. That would be even more comfortable now that we're doing it in base 10 than it was with the other bases. And the way that we've typically approached this, and you let me know if you see something that doesn't seem familiar or comfortable, but when I go to start this, I'll start out in the ones place and I'll have 9 and 8, that would be 17, but I can't put 17 in the ones place, so I put a 7 here and I carry 10 over to the tens place. It's important to note that what I've done here is I've carried 10 ones. Oops. Over to the tens column. Let me know if I say or write anything that doesn't make sense or feel comfortable, but that's what we did here. We had 17. Well, I took 10 of those ones. I had 17 ones. I took 10 of them and moved them over to the tens place. All right, now I'm going to add in the tens column there, and I'll have 1 plus 6 is 7, and 7, that's 14. But I can't have 14. I'll put 4 here, and I'm going to carry. And what I'm doing in that step is I am going to carry 10 tens over to the hundreds column. It makes sense. If I have 14 tens down here, well, I have 14 tens. Well, I'm going to take 10 of those tens and move it over here because 10 tens is the same as 100. And so it's the same value. Now I can add those. 1 plus 3 is 4, and 4 is 8, and I get 847. And that's our standard algorithm for addition. When we have more than can fit, we carry over to the next column. Let me know if you have any questions about that or any questions about this language that we carried 10 ones over to the tens column, and then we carried 10 tens over to the hundreds column. One thing I do want to say about this algorithm, and most of us are extremely comfortable with this, we've been doing it for a significant portion of our lives, and it's very comfortable. But it is a little bit counterintuitive. Here's what I mean by that. If I were to give you a stack of bills, ones, fives, tens, 20s, and hundreds, if you were going to start counting those bills, you probably wouldn't start with the ones. 1, 2, 3, 4, okay, now the fives, now the tens. You'd probably start with the biggest bill. You would probably start with the hundreds and then work your way down to the ones. One thing is a little counterintuitive about this standard algorithm, and it's the one we use, and it's great. One thing that's a little counterintuitive about it is that we start in the ones place. And we wouldn't do that if we were counting something like money. What I want to show you coming up are a couple of other ways to add numbers. You may love them. You can resist them at first if you want to. That's all right. But just different ways of adding numbers that go along with our standard algorithm. The first of those is called the partial sums algorithm. When we're doing the partial sums algorithm, something that's kind of nice about this is we go from left to right. The same way you would count money if you were handed a stack of bills, that's how we're going to add these numbers. And we're going to have 369 plus 478. So it's the exact same problem we did last time. All right, we're going to go left to right. So that means we're going to start in the hundreds place. And we're going to emphasize the fact that we are in the hundreds place. So that 3 right here, what is that? It's not really 3. What does that number actually represent? Not 3, but what? Because of where it is. Excellent. Katrina, Madison, Kate, you're exactly right. Perfect. So that 3 is 300. This 4 is 400. So when I add those together, I get 700. And then I move over a place. Okay. Over here in the tens place, this 6 represents 60. This 7 represents 70. So I'll add those together. 60 and 70 is 130. Okay. One more column to go. Finally, we get to the ones place. 9 and 8 is 17. So I'll just write down 17. And the reason this is called the The reason this is called the partial sums algorithm is that's exactly what we've got here. We've got a piece of the sum, another piece of the sum, and another piece of the sum. So it's called the partial sums algorithm. Now we'll add these. And again, we'll go left to right. 7 and 1 makes 8. 0, 3 and 1 makes 4. 0, 0 and 7 just makes 7. And there's our sum of 847. It's the exact same answer we got this way when we did the standard algorithm, 847. This way we did it using the partial sums algorithm, where we started on the left and worked our way down to the ones place. Let me know if you have questions on this before I give you a chance to practice one. Okay. 515 plus 377. I want you to try this one. 515 plus 377. Try to do that using the partial sums algorithm. I'm not really going to make a poll for this because I don't think you'll have any trouble getting to the right answer. I just want to give you a chance to write this one out using the partial sums algorithm, and then I'll do it, and then you can kind of see what does yours look like, what does mine look like, are there any questions you want to ask about this algorithm. Essentially, what the partial sums algorithm does is maybe you have a student who's kind of struggling with place value and you want to help reinforce that that 5 on the top left there is in the hundreds place, so it means 500. The 3 is in the hundreds place, so it means 300. This is a great way to emphasize place value if a student's having trouble with that. If a student's having trouble with the standard algorithm, you might let them do this one for a while. I think eventually you want to get them comfortable with the standard algorithm, but they could start here until they get kind of comfortable with what's happening with all the numbers. Okay, let's see what this one looks like then. Starting over here on the left, because that's how partial sums works. We go left to right. 500 plus 300 would be 800. And then moving over a column to the tens place, we have 10 plus 70 would be 80. And then finally 5 plus 7, that's 12. Now we'll add these, and we'll have 892. Depending on what the numbers turn out to be, you may have to continue further down. I kept these pretty brief so we could just fit them on one slide. But if this had been an 8 and a 4, and you have, well, that's 80 and 40, that's 120, and you just have to keep going down until you get to where you don't have to do that anymore. I kept these short so that they would fit nicely on the page. Any questions about the partial sum algorithm? And you're allowed to make comments too. Like, I think starting in the hundredths place makes a ton of sense. Or, I don't like this so much. You're allowed to think those things. You're allowed to say those things. The next one coming up, I think you'll like very much. The lattice method for addition. So if any of you have ever had a porch that was kind of elevated, or seen a house with a deck that might be off the ground a few feet, they might have lattice underneath it that kind of goes down to the ground to sort of obscure what's underneath the house. That's kind of what's going on here. We are going to make a lattice to help us add these numbers. And if we're going to add 369 plus 478. So we're back to that same example we've been using all day long. What we're going to do is, yeah, we're going to put a line under here, but what we're going to do is we're going to make boxes. I'm going to put a box under the ones place, a box under the tens place, and I have a box under the hundreds place. And then I'm going to cut these in half. So I'm going to cut this in half and extend that line down. Cut this in half and extend that line down. Cut this in half and extend that line down. And that's how this is the lattice method. We've created this lattice here that we're going to use as we add these numbers. And what's cool about the lattice method is it takes care of the carrying for you because we drew it this way. Here's what I mean, and here's how it works. We start in the ones place. 9 and 8 is 17. That's 17. We'll put the 1 that's the tens over there, and the 7 ones go down on the bottom. We'll do the same thing in the next column over. 6 and 7 is 13. 1 and 3, because it's 13. And then 3 and 4 is 7. We just put the 7 down here at the bottom. We don't have any tens in that one. Okay, now what we're going to do when we go to finish this is we're going to add along those diagonals. Here we just have a 7. 1 and 3 makes 4. 1 and 7 makes 8. And there's our answer of 847. The lattice down here takes care of the carrying for us. When we did 9 and 8 is 17, when we put that 1 in this position, we were essentially putting it in the tens column. when we did 6 and 7 is 13 and we put this 1 here, we were essentially putting it in the hundreds column because of those diagonal lines. And then we get 847. We don't have to think about carrying. It's built right into the picture. Are there any questions about this before I have you try one using the lattice method? Okay. I want you to try 277 plus 358 using the lattice method. I'm not going to make a poll because I'm pretty sure you'll get the right answer, but I want you to just take a minute, see if you can set up the lattice and add these two numbers using the lattice method. Here again, this is a different way of adding numbers. It's an algorithm. It works every time. That if you have a kid that might be struggling with the standard algorithm, you might want to try this. It takes care of the carrying for you in the diagram, and it's a great place to look at. See, we had 17, so this 1 has to go over to the tens place. And eventually you work your way back to the standard algorithm from here. I think it's a terrific teaching tool. You don't have to agree with me also. I want you to know partial sums. I want you to know lattice method. You can love them or you don't have to. It's all right. Okay, let's see how this goes. So I am going to draw my box down here and section it off into ones, tens, and hundreds. And then I'm going to draw in my diagonal lines that's going to take care of the carrying for me. Oh, awesome, Laura. I think a lot of people like the lattice method. So that's very good. So 7 and 8 is 15. So 1 up here and 5 down here. And we've put that 1 over in the tens place, but we didn't have to think about carrying it. Then 7 and 5 would be 12. 2 and 3 would be 5. And now once we're done with all that, now we add along our diagonals. And this way we just have a 5. In this one we have a 1 and a 2 is a 3. This way we have a 1 and a 5 is a 6. And so our answer here is 635. Essentially, the lattice builds out our place value positions for us. That's the value in the lattice method. Let me know if you have any questions about lattice method before we move away from these alternative algorithms. We'll see some alternative algorithms as we go through our study of the arithmetic operations. Okay, terrific. Mental addition, doing something in your head. So if we want to add something, but I don't have any paper, I don't have a calculator handy, my phone battery died, whatever it is, and I want to add 68 plus 35 mentally. There's a couple of different ways that we can go about that. One way is called leading digit addition. And what we do there is we just sort of break this thing apart. It's almost like partial sums. Because what I'm going to do is I'm going to look at 68 and I'm going to go, well, that's a 60. I'm going to look at 35 over there and say that has a 30. And then I'll go back and pick up the 8 in the ones column and I'll pick up the 5 in the ones column. Because now I can do this in my head because I can say, well, 60 and 30, that's 90. And 8 more gives me 98. And then 5 more on top of that is 103. By breaking this apart and looking at the leading digit, I can sort of do this with partial sums in my head. 60 and 30 is 90, 8 more makes 98, 5 more makes 103. Another approach to mental addition is called compensation. This one's kind of cool because it leads into what we're going to do, solving equations way down the road with kids. But the idea is we start out with 68 plus 35 and we think, okay, well, I can't do that in my head, but I can make this 68 bigger by 2 as long as I compensate by making the 35 smaller by 2. So in my head, I'm turning that into 70, but to keep this thing balanced, I need to drop that by 2 and turn it into 33, and 70 plus 33 I can do in my head. That's 103. That's called compensation. So leading digit is kind of like partial sums. Compensation, we make one number bigger, make the other one smaller by the same amount so that they're numbers that are easy to work with. Break and bridge is very similar to leading digit. Break and bridge, we're going to take 68 and leave it alone. The 35, we're going to break apart. We're going to make it 30 and 5. And the reason for that is then here, well, 68 and 30 I can do in my head. That's 98. And then I have 5 more to go to get to 103. Those are just 3 different techniques that can be used for mental addition. I kind of think the most clever is compensation, but all 3 are good. Honestly, if I'm adding 2 numbers up, I'll kind of do this leading digit thing automatically in my head. If I were going to add these 2, I'd go, well, 60 and 30 is 90, 8 and 5 is 13, so it's 103. It's pretty much what's going on with the leading digit approach. Let me know if you have any questions about any of those. And basically, it's just knowing what these are, knowing that they're out there as ways to add mentally. Estimation. A key about estimation is that we are not after an exact answer. We're making an estimate. We want something that's in the ballpark. It doesn't have to be perfect. And so leading digit estimation is all you do is take the leading digit. So that first number I have there, 45,327. What is the leading digit? It's that 4 in the front, so I'm going to call that 40,000. And then the second number, 33,518, just after the leading digit, so I'm going to call that 30,000. And so my estimate, my ballpark here then is 70,000. Not an exact answer, but if leading digit estimation is good enough, then that estimate is good enough. One thing I want to say about leading digit estimation is you'll notice we're just kind of dropping all of this, everything but that first digit. So it's always going to be smaller than the actual amount because we're dropping all the place values after the first one. So it's going to be a smaller number than the actual amount. A little more precise than this would be rounding, and we decide where we want to round. Let's say we want to round to the nearest 10,000. So I'm going to take 45,327 and I'm going to round that to the nearest 10,000. So I'll find the 10,000s place and I look to the right. That's 5 or bigger, so we'll round this up to be 50,000. And then I also want to round 33,518 to the nearest 10,000. So we'll find the 10,000. We'll look one space to the right. That's 4 or lower, so we'll round this down to 30,000. And now to finish off my estimate, I'll add those together and have 80,000. Rounding is a little more accurate typically than leading digit because we don't just drop off whatever's after the first number. We have to be told where to round. And keep in mind, when we're doing estimation, we're just looking for an estimate. It's not the exact correct answer. It's something that's in the ballpark. These 2 different approaches to estimation are both completely valid, and these ones give you different results because, well, we were told to do a different thing, so we got a different outcome. Let me know if you have any questions about any of that. Okay, one more type of estimation to look at, and it's compatible numbers. This is a little bit like the compensation approach for adding numbers where we would, well, if I make this one a little bigger and I make that one a little smaller, it's going to work out. There's something like that here where we have a strategy going in. And the idea of compatible numbers is you look for things that go well together. That's what makes them compatible. And what I mean by that is when I look at this number, and you may not see it exactly the same as me, but well, this 27 and that 75, that's pretty much 100. Again, this is an estimate. We're not after an exact answer, but 27 and 75, that's pretty much 100. And then 161 and 34, well, that's pretty much 200. And I'll add those together and have an estimate of adding those four numbers of 300. The compatible part is I look for things that take me to an easy place. And then in here, those two took me to an easy place. The 161 and the 34 took me to an easy place. And then I could add the easy numbers to get one that's an estimate. Techniques for estimation are great for us to talk about, but to be completely honest, they don't make the best quiz and exam questions because an estimate doesn't have an exact answer to it. So I want you to be aware of those. I want you to be able to do practice problems with those. But as far as quiz and exam question goes, estimation, not something I'm going to focus on. All right. Last thing I want to say is in your homework, number 18 says that you're supposed to use the lattice method. You don't have to use the lattice method. You can if you want to,